corporations and research institutions worldwide are making significant investments in this field. And as educators, it is our responsibility to stay ahead of the curve so that we can prepare our students for the opportunities and challenges ahead. This faculty development program has been designed to equip us with the fundamental knowledge, our foundational knowledge, practical insights, and research perspectives needed to understand and teach the quantum computing effectively. Over the coming sessions, we will explore not only the theoretical underpinnings, but also the tools, the simulators, the programming frameworks like Qiskit, Circuit, etc., that are enabling the hands-on experimentation in this cutting-edge domain. I encourage all the participants to make the most of this opportunity, ask the questions, engage in discussions, and think about how we can integrate the quantum concepts into our curriculum and research. Let us together take the step into the quantum future, one that promises new possibilities and demands fresh perspectives. I thank the management, the principal and director of SRK Engineering College for providing support or given us the support to organizing this faculty development program. Thank you and I wish the program a great success.
Thank you, sir, for your encouraging words and for your constant guidance in making programs like this impactful. Now, to invite our distinguished resource person for today's FDP, I request my peer Hamant to kindly take over the proceedings and extend the formal invitation to Dr. Chandrasekhar Oruganti, sir.
Good evening, everyone. It gives me a great honor to introduce today's distinguished guest, Dr. Chandrasekhar Origundi. Dr. Chandrasekhar Origundi has completed his master's from Dhirubhai Ambani University, Gujarat. Before pursuing his PhD, he worked for 8 years at Infosys as a team lead. He then pursued his full-time PhD at IIIT Sri City, specializing in deep learning. During his period, he was a visiting scholar at IIT Madras, IIT Tirupati, and IIT Indore, further enriching his academic exposure. Since 2020, Dr. Origundi has been working as a lead computer vision engineer in one of the world's top semiconductor-based companies, contributing to real-time deep learning products. With nearly 15 years of IT experience, he has taken up various roles such as lead engineer and AML product consultant. His research contributions are exceptional, with more than 125 publications and prestigious conferences like ICDAR, IJCB, WACV, CVPRW, ICCVW, and reputed journals such as Neurocomputing and Neural Computing and Applications. He is also a regular speaker at ML and DL events in premier institutions including NITs and IIITs, having conducted over 100 sessions that have inspired many young researchers. We are truly honored to have such an accomplished personality with us today. Now, I humbly invite Dr. Chandrasekhar Origundi to share his valuable thoughts with us.
Good evening all. Good evening to the HOD and good evening to the participants.
Good evening, sir.
Good evening to the coordinator. Thanks for inviting me and thanks to all the participants. So today, the first day we are discussing about the introduction. So I will try to introduce the subject, all the basic and advanced concepts, so that you can able to follow the later topics. So let me share. So first I want to you to get the difference, what actually the classical computing and what actually the quantum computing. So first, if you see this slide will tell you why we need quantum computing. So we know that if you use our laptop or a desktop machine, so it's very easy to solve this problem. So the computers can able to answer this problem very easily, 3 into 2 equal to 6. And if you want to factorize also, either the product here or if you want to factorize, the systems can do it quickly and faster. But as the number increases, see here, units, tens, hundreds, thousand, 10,000, lakhs, 10 lakhs, crores. So this is almost 7 crores, means 37 crores, 737 crores, 7,000, lakhs, means 8 lakhs crores, 8 lakhs crores. So this is a simple 6, this is 8 lakhs crores closely. So if you want to factorize, no classic computer can do this. Even if you use GPUs or supercomputers, they can solve, but it will take time, maybe 1 year or say 6 months to solve this problem. But the quantum computers can be able to factorize and solve this problem within minutes. So these are the places where we need quantum computing, where the domain space is extremely high. For simple computations, we don't need any quantum computing. So where I need to go through all the possible values, say password. So if my password is length, my password length is 1 bit. So suppose if I'm considering letters plus digits. So 27 plus 10, 37 combination, a single digit. So if I try 37 combinations, I can be successful. Suppose if it is 2, okay, with repetition is allowed, 37 into 37. So these are all the possible combinations. But still I can able to achieve maybe within 10 minutes. And as my password length increases, the time taken to crack it increase. Suppose if it is of 50 bits, suppose if I chosen my password length 50 bits, okay, then if I want to crack that password, 37 into 37 into 37, 50 times. So these many attempts, first attempt to these many attempts I need to do, 37 to the power of 50, which no supercomputer can afford or can able to solve in a day. It needs some time, maybe months or hours. So if my volume space, the oracle is large, then we need quantum computers, because it has to solve the complex problems. The way it treats, means the way it represents the data, the way it processes the data, the way it stores the data.
Sir,
Excuse
sir,
me.
Chandrasekhar, sir. Sir,
Yes.
sorry for disturbing you. Sir, voice is very low, sir. Please be low, sir.
So I made it 100%. Is it same for everyone?
Yes, sir. We are also facing same.
Yes, yes. Not getting clear.
So please adjust your mic, sir.
Is it clear now? Okay, apart from Vinod Babu, can anyone confirm? For him, okay, fine.
Yes, sir.
Sir.
So I'm just explaining. See, quantum computing is not a technology. Okay, so it is the technique where it will fasten the computations. That's it. So the problems like this, which we cannot solve by using a normal computer, we need to use the quantum computers. So quantum computers, as I said, if it has to solve these type of problems, first it has to solve. Second thing is it has to solve in a lesser amount of time, maybe 5 seconds or say 5 minutes, which the normal computers can take 1 year to solve these kind of problems. So they may take 1 year, but these quantum computers can solve in 5 minutes. So in order to do the massive computations parallelly, the way they represent the data, that means data representation, data processing, and data communication, all must be completely different compared to classical systems. See, in deep learning, we are using GPU systems. So we have a normal desktop or a normal laptop, but in order to process, say, 30,000 images, each of size 512 into 512, we are using GPU systems. But GPU systems are not much different compared to the desktop or a laptop, but they have some efficient memory management techniques. But quantum computing is completely different. It's not just an extension or in terms of computation or storage. Because see here, it can able to solve a massive computation problem with very less amount of time. So end to end will get changed. So the circuits, starting from the data, starting from the circuits, so we might have studied AND gate, NAND gate, etc. So those gates, the circuits formed with those gates, data communication, everything will get changed. Okay, so this is how quantum computing is different compared to the traditional systems. So if you are solving a problem which is not computation intensive, then a traditional system will work. But if you are solving a huge computational problem where the search space or the oracle is large, then we need quantum computing. Like suppose I will give an example. So I will give my Aadhaar face image as an input to the system. The requirement is it has to go through all the entities of the Aadhaar, all photos of the Indian Aadhaar, and it has to give the output, my address, etc. That is a requirement. So if we have close to 200 crores of images, 200 crores of images, each person in India, and takes a matching each system to one person, second, suppose each match will take, say, 1 second. Then to get the result, it has to sequentially process all the images. So 200 crores into 1 second is what the output time. Because the classical computing systems are sequential systems, one by one. So it will take 200 crores of seconds. Suppose then 200 crores, if I divide it by 60, it will be in minutes. If I multiply with 60, it will be in hours. Then if I divide it by 24, it will be in days. Can anyone tell me the answer? 200 crores by 60 to 60 to 24? Anyone? $200 crores divided by 60 into 60 into 24. Am I audible? Am I audible? Can anyone please confirm? Okay. So see, 24 crore, 200 crores. Okay, 200 into, okay, units, tens, hundreds, thousand, 10,000, lakhs, 10 lakhs, crores, 200 crores. This is the value. Okay, and these many seconds. So I want to divide it by 60 into 60 into 24. See, 200 crores divided by, sorry, divided by, so how many days? 2 lakh 31 days 481. Okay, so if I divide it by 350 days, see, 661 years it will take. If I assume that each processing, each system to map each photo, okay, means if it has to match photo, and it will take the first other photo, compare the distance, okay, next photo. So if I assume that in 1 second it will complete, it is taking some 300 years. But if you use quantum computing, of course we didn't use, but we can complete maybe in a week, worst case. So that is what the difference between what a classical computing and a quantum computing can do. So to achieve this, as I said, everything will change. It's a different world. The data representation, as I said, and the data processing, data communication, everything will be completely different. It's a different world. Fine. Okay, so with this, I think this is the last slide where we can discuss about the difference. So see here, everything in the classical computing is a brute force, or I can say sequential, one by one. But there are some algorithms, okay, like Shor's algorithm and Grover's algorithm, where I can achieve in square root of n time. I can drastically reduce the computation time. Okay, so parallelism is what the advantage of quantum computing. Here everything is serial and brute force. Okay, so these are all the things. Okay, so drug discovery, portfolio management, weather prediction, where the data is huge volume, then quantum computing comes into risk. Okay, so with this, now see here, so how we represent, okay, so see here, classical computers, the bits is the how we represent data. So we have 2 bits, either 0 or 1, and it means that variable, either it stores 1 or it stores 0. Okay, so bits are independent of each other. There is no relationship between bit 0 and bit 1. You can store either 0 or 1 at a time. That means, suppose x equal to 5, so x contains 5. Then if I replace x equal to 5 with x equal to 6, then x contains 6. We have an array. So what is the property of an array? So array can store, see, that number 1 to 10, correct? So 10 numbers an array contains. Assume that if my variable x contains like this, if I declare a variable and that variable contains like this, not only 10 elements, if I can able to store, say, 1 lakh elements at a time, I can parallelly access whichever number I want. Then obviously I can increase the computation, means the parallelism I can increase. So every algorithm focus in quantum computing, they focus on how I can improve the parallelism in terms of data storage, data processing, data communication also. So you got this point. So if x is a variable, in classical computing, I can store 1 at a time. And if I replace with x, now x contains 6. We have arrays in C language. Okay, so array can store any number, but if array is a special variable, but what I want is for this variable only, if we get such a property where I can store n number of elements and parallel I can access any element. So that's how it speeds the computation. So when it comes to quantum computing, so quantum computing is largely inspired from, it takes the concepts from the quantum physics and quantum mechanics. So everything is a in quantum computing. So I will move in some, okay, so because I keep on pasting the new content. So if you see here, the quantum computing inspires from quantum mechanics is that we depends upon tiny particles like photons. So we always deals with the fastest transmission particles, the particles that make up light. So light is a collection of photons. And we also deal with the inside an atom, not an atom, inside an atom, like protons, neutrons, and electrons. So in the classical computing, we are thinking about the voltage. So if voltage is high or voltage is on, it's a some bit 1. If voltage is down, it represents some bit which is 0. Okay. So here, because we have to deal with huge computations, as I said, it will take some hundreds of years for the other problems if we use the classical system, and if this quantum computing can able to do it in a very short time. So see, the way we represent the data is completely changing, and we are depending upon the photons, which are having the fastest communication properties, and the electrons. So electrons are having the spinning property. So electrons have spin property. We all studied in our intermediate. What is meant by spinning? Like a fan, it's continuously spinning. So electron, maybe this is in 0th state, this is in 1 state, and if it continuously spinning, we cannot say which state it is. It will be in both states parallelly. Okay, so it is a complete different study where we brought in the concepts from quantum physics and quantum mechanics, and we are using the photons to store the data, new electrons to store the data. Okay, so any element which is having the properties to store more data once, so those entities we are considering to store our data. Example, electrons. So electrons is having a spinning property. Okay, I will show you. So this is, suppose if it's 0th state and 1 state, if it is continuously spinning faster than 10 times faster than the fan, then it contains both. But when you stop it, it interferes to either 0 or 1. Okay, so that's how quantum computing inspires from quantum physics and quantum mechanics. So if I show that, okay, so like this, so it will be in 0th state, and 1 is the qubit. Here we will call it as a qubits, quantum bits, and here we are calling it as a bit. So 0 and 1, or we may have 2 qubits, 3 qubits, etc. But if you consider 2 qubits, so we have this value, 0 or 1. Okay, so we got the entire quantum computing, as I said, inspired from quantum physics and quantum mechanics. It borrowed 3 topics. One is superposition, second one is entanglement, okay, entanglement, and third one is interference. So these 3 properties it taken from the quantum mechanics. So these 3 forms the pillars for the quantum computing. See here, many states at a time. So it can able to, like this, it can able to hold many states at a time. But array is different. See, array property is like this, but we want the variable to have such a property. In C language, a normal variable contains only one value. But assume that if that value, that variable is got the capacity like to store multiple values, and parallelly it can able to deal any of the value. So such flexibility is what? Many states at a time. Okay, so that is called superposition. Okay, so one state at a time, one value at a time. And in quantum computing, because of we need to handle massive computations, and that too with a short span of time, we need to handle huge volumes of data at a time. Okay, So there are some examples, advantages wherever there is a data, okay, such means the space, okay. So there we can apply quantum computing. So okay, so if you see here, one more example, a classical maze problem. Okay, see here, it can only one path, it can check only one path at a time, and it can compute for multiple paths. Okay, suppose see, what is this maze problem? Somewhere we will start it here, and we need to find out the path, okay, which is the correct path. So how we will do? So first we will start it here, and then we will try to check one path, second path, third path. So one by one, sequential, 1, 2, 3. But in quantum computing, how we will do is at a time, one value we check like this, another one, okay, another combination. So this like this. So at a time we can do the same task. So here first we'll try one path. Suppose if I want to tell in terms of a for loop, in classical computing we will print 1, 2, 3, 4, one after the other. Assume that for loop at a time, while the time taken to print 1, we can able to print 1 to 9 at a time. So the values, there is a quantum mechanics, that superposition property makes us to pack multiple values as a single variable. Okay, so Gotham, Telugulo చెప్పాలంటే మన దగ్గర గోతం ఉంటుంది. ఆ గోతం is a quantum computing. We can put all balls, all values together and carry. In classical computing, చిన్న soap box, ante only one value. Because I can able to handle these multiple values at a time, obviously I can compute faster. Okay, so that what makes a difference. But how to hold multiple values? That's what is a challenging also. So that's what the first property is. This I will share, so you can just go through it. So the first property is the superposition. Superposition means, as I said, quantum computing entire thing is a basket where it can hold multiple values at a time, multiple balls. You can pick up any ball at any point of time. So if you see the binary system or the existing systems, either it contains the value 0 or 1, but there is no intermediate representation, or there is no multiple values together. But here if you see, this sphere is called as a score sphere. Score sphere, where if you see, I am representing the value 0, the qubit 0 here, and qubit 1 this side. So by varying the combination, by varying the value proportion of 0 and 1, I can create any position. So if you see here, see, these are all the possible positions. So if I just I can just show in YouTube, you can understand. Okay, so there is one video. Okay, at a time it will keep on moving. Okay, so let me show that. See here. So at a time, so one direction is one representation. Combination of these two, 0 and 1. See, 0 and 1 remain same. Okay, let's see this video, and then I will explain. So each direction, each value is one combination of 0 and 1. Okay, so this is a sphere. So on top of it we have ket 0. So in quantum computing we call this representation as a ket 0, and this is ket 1. Okay. Now what I can do is I can in the sphere. Okay, if you take a sphere, so there can be a line here or here. So if you take any line, if it is here, the 0, this contribution is 0, and this is 100%. Okay, and if it is like this, then this value is 0 and this is 100%. So by taking the combinations, see now like this. Okay, now if it like means some combination of 0 and some combination of 1. So that is how you can represent the data. Okay, only 2 values, but you can create any combination. So if it is like this, means this line represents some combination of 0, that means this value, plus some proportionate we are combining this value, and those values are called as alpha and beta. The condition is that alpha square plus beta square must be 1. This is the condition. So this combination I will represent with a new variable called psi. And because this plus, that means this psi contains some representation of bracket 0, ket 0 and ket 1. This plus represents the superposition, and this psi equal to this value, this line, which is some combination of this and some combination of this. When I say combination, those are alpha and beta. The condition is that alpha square plus beta square equal to 1. Now tell me, what could be alpha and beta? What are these alpha and beta? When their summation, when their sum is expected to be 1, so what alpha square and beta square represents? What this alpha square and beta square represents? They represents the probabilities. Okay, so okay, what it means, what is alpha square probability? So when I say that, if I want to combine, if I want to represent, if I want to push అంటే ఈ రెండింటిని కుట్టి ఒక దాంట్లో పెట్టాలంటే, so I am taking some combination of alpha and some combination of beta, and I am telling that if I want to do the superposition, the condition is alpha square plus beta square equal to 1, and I am telling that these are the probabilities, so that their summation equal to 1. Okay, then what it represents, that psi, that means, so psi, and if I take this as a box, alpha means 0. Okay, say 10%, say 10%, 0.1. This beta may be 0.9. That means the combination, in the psi combination, it contains both alpha and beta in some proportion. But one more condition, the main condition is, it doesn't mean that it always contains these two, but when you try to measure or when you try to use this psi in any of the computations, say psi into 0.1, this psi must break down, converge to either 0 or 1. But psi contains both. See, this basket contains many balls at a time when you are taking. But when you try to pick it up one ball, okay, you will get only one ball out of it. So this psi is this one of the ball is bracket 0, another ball is bracket 1. So you combine them to form a basket. But when you try one ball out of it, you won't get two balls, you will get only one value. Either you will get bracket 0 or you will get bracket 1 into, you will do whatever multiplication or whatever operation you want. This is convergence. But this alpha square and beta square tells that when I use psi, the probability that psi converges to ket 0 is alpha square probability, and the probability that psi converges to 1 is the beta square probability. So this is in brief about this superposition and how you can combine this. So any questions in this? This is very much important to understand. So plus means you are adding psi 0 and psi 1, and here this line represents the combination. How much? This is psi line. How much it is? Okay, so it can vary. It can vary like this. Some combination of 0. Here it is 1 is 0, and if it is like this 0, this ket 0 is 0, no contribution. Apart from that, some combination of 0 and 1 is what happening. But when you measure into some operations, it will break down to one of the combination. And we cannot say which one, but this alpha, and based upon the alpha square and beta square, we can say that whichever is value, most probably that value it will be converged. Like onion movie. He is having both Ramu and Remo. He is having both characteristics. But when we talk to him at a time, either Ramu is talking or Remo is talking. But but he never shows both the properties. But he is having both the properties. Same. This is ket 0 and this is ket 1. Both are there in the psi. But when you use psi for multiplication or any operation, either you may get psi 0 value or you may get psi 1 represented by this value, ket 0 or ket 1. But the psi contains both. When you use it for computations, you will get only one value. But what is the probability that you will get this or this depends upon the coefficients you have used, that is alpha and beta, and the alpha square and beta square is the probabilities. Whichever is higher, most probably psi may converge to that value. Is it clear? Any doubts? Okay. Then, okay, so that is what they are representing here. Okay, multiple values. See, it can sphere. Okay, so can anyone tell me, any mathematics or students, what is this circle and what is this circle? What is this circle? What is this circle? What is this circle? Please think of it. We will come to that part later. Okay, so see here, depending upon the combination, so there is a chance, 25% chance that, suppose if I am dealing with 2 qubits, this is 1 qubits, means either 0 or 1. If I can able to deal with 2 qubits, see, n qubits means 2 power n possibilities. Suppose if I am dealing with 1 qubit, that means 2 to the power of 1. What are those values? Qubit 0, qubit 1. So when I am dealing with 2 qubits, qubit length, then I can able to handle 2 square values, which is equal to 4, which is equal to 0, 0, 0, 1, 1, 0, 1, 1. And if I want to handle, that means I can able to handle these all 4 together. That means, now tell me, see, if I'm dealing with 1 qubit, okay, here if you see 1 qubits, how many combinations? You forget about the path. How many combinations? 2 to the power of 2 power n combinations, which is equal to 2 to the power of 1, which is equal to 2 values. What are those? Ket 0 or bracket 0 or 0, because quantum computing, if that context is fixed, I can say bit 0 and bit 1. Okay, so this is bit 1. So 0 and 1. Now, if I make 2, n equal to 2, so n equal to 2 means 2 square, which is equal to 4. So I can handle 4 values of length 2. If of length 2, that means what are those? 0, 0 of length 2. Like this, I can handle 4 values. What are those? 0, 0, 0, 1, 1, 0, 1, 1. 4 values I can handle at a time. Suppose 3 qubit quantum computer. 3 qubit quantum computer means 2 cube, 8 values. So 0, 0, 0 to 1, 1, 1. 8 values I can handle at a time. Okay, so 8 values, that means the classic computer can be able to store 1 value at a time, And if I assign the next immediate step, if I make it x equal to 6 in the C language, now my x contains 6. When we think in the quantum computing language, I can make x to contain 8 values at a time. If it is a 3-bit quantum computing, okay, so 0, 0, 0 to 1, 1, 1, 8 values it can handle parallelly. So in that Aadhaar card example, so 1 image to 1 write, so it can handle 8 images at a time. Similarly, 4 qubit, okay, 4 qubit means 16 values I can handle at a time, 1 second. So classical computing can do 1 operation, whereas I can do 2 to the power of n operations, where n is the number of qubits. Suppose if I have 4 qubit quantum computer, I can handle 16 operations at a time because I can hold 16 values. Now, if you see in Vijayawada, so CBN is planning for Quantum Valley. Okay, so let's see what is the system they are bringing. Okay. So if you see, so IBM and partnering to establish India's largest quantum computer in Amravati, featuring 156 qubit. So 156 qubit they are planning to deploy. So 156 means how many values at a time it can handle? How many values? This n equal to 156. If it is 1, 2 values. If it is 2, 4 values. Then if it is 156, then 2 to the power of 156 values it can able to handle at a time. Okay. So what is 2 to the power of 156? So we know that
Sir, not audible, sir.
Sir, we can't hear you, sir.
oh, sorry. No, I don't know who muted this. Okay. Is it clear now?
Yes, sir.
Yes, sir.
So they are deploying 156 qubit. That means I can able to handle 2 to the power of 156 values at a time. So what is that value? 2 power 10 means 1024. Like this, if I multiply for 15 times, then it will become close to 150. So 1024 into 1024 into 1024, like this, 10 times I have 15 times I have to do. So those many numbers it can able to handle, which is like storing. We can represent each sand in a beach, each sand in a Vizag beach or Bhimavaram beach. Okay, so that is the power of quantum computing. See here. See, and many states at a time. It's not just storing, but all those values I can represent at a time parallelly. Whereas the classical computers, they can able to handle one value at a time. So there is no scope for parallelism. Okay. So this is all what we discussed: quantum computers, superposition, multiple states. So these are the 3 properties is what inspired from quantum physics and mechanics. Superposition is just now we discussed. We will discuss other things, entanglements and measurement. See, what is measurement? Collapsing qubits into definite outcomes. So qubit means, so whenever we do superposition, as I said, it will contain both 0 and 1. But when you use it for computation, it will collapse into only one value. And which value is? That's what defined by the alpha and beta. So this is the NPTEL slides. Okay, some computation. What is the need for computation? Okay, so qubit. So see here. Now, how to represent? So if you see this color, so this color is, say I have like this, one red value. This is blue value. That means get 0. Suppose superposition means, so 0. Say that 0 is red color, like this. This red color is 0. And this blue one is, say, 1. So this is what the combination. I combined this and this to form this ball. So this is the psi value. So psi value is a combination of ket 0 and, sorry, ket 0 and ket 1. Okay. What is the probability? Is what alpha square and beta square decides. So this is the probability. So red is more, that is alpha square, and this blue is beta square. So alpha square plus beta square is what the psi value, and the condition is alpha square plus beta square equal to 1. So there is higher chance that we superposition this. There is high chance that if I use psi in computation, it collapses into which color, which value? Which color? More is red color. So it collapses into red value. Okay. So that is the superposition. So if you see here, this quantum physics and quantum mechanics inspired by or dependent on the photons and inside atom like electrons. So if I want to represent two values at a time in quantum computing, I also need to look for the elements having such properties. So electron is such property where, see, 0, this is in one stage, parallelly, high level, low level. Okay, so parallel, see, at a time it can be in two states. It is having a property of spinning. Fastly it can rotate. So I can use electron to represent my values ket 0 and ket 1. Is it clear? Is it clear? So why I need electron? Why we are depending on the electrons? Because for 0 and 1 in classical computing, we are depending on the voltage. But here, I need some elements, okay, so which can have dual property, which can able to store two values. So electron is having such property. So if I want to represent the ket 0 and ket 1, I will choose the electrons. So electrons are having the dual state and spinning property. Okay, is this clear? Any doubts? Anyone? Okay. Okay. Next, entanglement. See, entanglement is also, see, here it's like a movie. We cannot cross check everything because, see, we are depending upon the photons and the electrons inside atom. Okay, so we just have to trust. So what is meant by entanglement? So we just studied superposition. So superposition means I have to combine both the parties, both the values. Okay, like this. So electron orbit, same thing here also. Entanglement. What is meant by entanglement? You can correlate, you can link two values, two qubits, two entities. Okay, so there is a, suppose, assume that, one example, you went to a shop and you have taken two things. So one is apple, second one is banana. You just asked the shop guy, so he given these two, but you don't know what is inside. He given two packet. But once you go home and you open the packet, if you see apple, and you will say that the other one is banana. Correct? They are linked. Same entanglement is also like this. So two entities you are linking together. And how that link forms, it's like light connected through light. Okay, so if you see, so while entanglement is a remarkable feature of quantum physics that connects particles in a seemingly mysterious way, they themselves claim that it's a mysterious. So how they connect? If somewhere, if you entangle them, that means entanglement, if you combine them, if you know one value and you can say the another one value, that is entanglement. And even though they are far separated, one is on earth, another one is on moon, they will bound to that. Okay, see here, entanglement. Okay, so means how you entangle them. Two things. Suppose if you make one box with quantum 0 and another box is quantum 1. Okay, so by looking into this one, you can say that the other box value, and these values never change. That connectivity, see here, entanglement is a uniquely quantum phenomena where two particles, qubits, are strongly correlated. They are linked together. Their behavior is linked. Hello, brother, movie, even if separated by vast distances. See, their actions are dependent on each other. If one spins, the other responds accordingly. If one changes, the other one also changes. It has to respond for this action. So in contrast, the individual represents non-entangled state. That means there is no relationship between classic bit 0 and classic 1. So if I change bit 0, if I change this value to 1, okay, this 1 never becomes 0. That means these two values are completely independent. But in case of quantum computing, what we can do is you can create entanglement. If you change one value, automatically the other one will also change. So entangled qubits do not have independent states. Okay, instead their joint state cannot be described by individual states. Measuring one instantly affects the other. So if you measure one value, automatically I can compute the other value. No need to compute the other one. Automatically I can get the value. Okay. So somewhere I explained this. Okay. See here, entanglement does not involve sending a signal from A to B. You no need to send. Once you connect them, once you connect two entities, okay, so automatically, okay, so if you see here, in classical computing, there is no dependency. If you if you toss two coins, there is no correlation, independent. But in quantum computing, what you can do is you can combine these qubits. So if one changes to 0, automatically this 0 changes to 1. So that relationship, if you make, that is called as entanglement. Okay, so you are linking. So 1, 1. Okay, so if it changes to some value, then automatically this will also change. So you are linking these two values, and this impact occurs even those two values are separated, earth to moon, north pole to south pole. Irrespective of the distance, you can impact, you can create two qubits. This may be 0, this may be 1, but you can connect them. So if this value changes, automatically this value changes. Okay, so that is one property called as entanglement. See here, if Alice measures her qubit and gets 0, automatically Bob will get 1. Some linking. If Alice value changes, Bob will get 0. That means that's how you are combining them. Okay, so that is one thing. Next, this wave property is simple. Okay, no need to worry now. So let's discuss about next. When we come to the representation, okay, mathematical aspects of quantum computing, so vectors plays a major role because this is a sphere, square sphere. So we are assuming that this is ket 0, this is ket 1. And if you create any vector here, okay, this is a vector. This is also a vector. This is a vector. So this entire quantum computing is vector study, is vectors. So based upon this superposition, this value, when I say superposition equal to alpha into ket 0 plus beta into ket 1, okay, this is a vector, this is a vector, okay, this is also a vector. Okay, so vector, we all know that it is having both magnitude and direction. Okay, so this is a vector, and the magnitude is 2 square plus 3 square. Okay, so for 2D, what is the magnitude? Okay, 2D vector example. Okay, this one. And what is the direction? So direction equal to, this is x and y, direction equal to theta of tan inverse of y by x. So as I said, everything, see here, everything, this is a vector, see, this is a vector. And this is ket 0, and this is ket 1. So there is a vector, which is a combination of ket 0 and ket 1. This is called as psi, which is equal resultant of superposition. So this quantum computing is completely a vector space analysis. So you can add two vectors, we can multiply this by a scalar. Okay, so all those things we can do. So this qubit, see this line is this line. This is a vector. Okay, and we all know that in this vector space, when we talk about this qubit vector space, this basis vector. Can anyone tell me what is the basis vector? What is the basis vectors? Anyone? Yes, huge memory, but they will maintain parallelism. But obviously, yes, we need a huge memory. So what is meant by basis in vectors? Anyone? Am I audible? Fundamental vector, yes, very good. Okay, so what is meant by basis means? Basis, okay, see here. Basis means, so in qubits, in quantum computing, ket 0, this I is a vector and J is a vector. So in quantum computing, this is called ket 0, this is called ket 1. So when whatever we're discussing, the qubit 0 and qubit 1, these are the basis vectors. Okay, so this is ket 0, value is this one, and where it will be at the north pole. And what about the ket 1? This is at the south pole. So this is one value, this is another value, and you can create by adding or by scalar multiplication, see, multiplying with the scalars, or by adding these basis vectors. You can use these basis vectors, that means these qubits. You can you do any arithmetic operations, and the resultant value will also be somewhere here. It will be in this sphere only. Okay, so that is the curve. Okay, next, let me go to that. See here, the basis vectors. So ket 0, the qubits are the, when we want to visualize, when we want to perform operations, okay, this qubit represents the 1 0 and qubit 1 represents the 0 1. So these are all the unit vectors and they are orthogonal to each other. So see here, they span the space. So by using the combination of ket 0 and ket 1, I can create any other, means the superposition vectors. So in quantum computing, these are all the basis vectors. Okay. See, are the basis vectors of the qubits space. And what about this C square here? C means a complex network. So I'm using this alpha and beta. So alpha into ket 0 plus, whenever you see plus, it is a superposition, you are combining. And I by root 2 is beta. This is beta into ket 1. Some combination we are creating to form a superposition vector set. And what is the condition? Square of this plus square of this must be equal to 1. Okay. So these coefficients alpha and beta, when you are dealing with real space, they can be scalars. And when you are dealing with a complex numbers, complex space, then those alpha and beta can be a complex numbers. Like this. If you represent those vectors I and j like this, but if you take if you want to represent these numbers in a complex space, these are like this. Okay. So now if you see, if I, as I explained, if I take qubits 1, 2 power n are the possible values I can represent at a time. So 2 power 1 means 2. Those are the values. What are the values? These are the values. And if I take qubits equal to 2, 2 square equal to 4. So all these 4 are the values I can represent. Similarly, 3 and 4, etc. Okay. So as I said, see here, we are using electron. So electron can, see, if it is in excited state, electron is always moving, and see, it is excited state, it will be in this row, and if it is a ground state, it will be in this row. So 2 values I can use to represent the electron. So electron, if it is in this state, this last this circle, so I can say that it representing the 1 value. And if it is in the inside this side, I can say that it is representing the 0. Clear? So this is completely, the quantum mechanics and quantum physics and quantum computing is completely depending upon the photons inside atoms. Why? Because I need such properties. What are those properties? An element must stay at 2 values at a time. That's why parallelism occurring. Simple unit of parallelism is electron. On top of this, I can build a whole complex parallel system. Okay. See here, low voltage and high voltage at a time. Okay. So all these things we study: superposition, entanglement, and measurement. So in superposition, what we are going to do, as I said, we are going to add some proportionate of 0, some proportionate of 1, and having the condition that the coefficient square must be equal to 1. That will be my superposition value. And this is represented in which space? Real number space. You can also represent in the complex number space. See here, this will be bit 0, this will be bit 1. But when you do this superposition. See, when you do this superposition, electron, now it is in both the states together. So that's why we are using electron to represent the data. So we are using voltage to represent classical bits. Here we are using electrons or ions, some other also possible, but electrons are used to store, to means to represent the data. Okay, at a time it is in low state and excited state. So excited states I can represent as a qubit 1, and the low state I can represent as a 0 for 2 values. Okay, like this I can increase the number of values. Okay, not only electrons, as I said, ion traps I can use to represent qubits. And those ion traps, not all ions, calcium and ytterbium are the ones which are having the dual property. Whichever elements which have the dual property, I can take them and I can use to represent the values. So all those things, neutral atoms, superconductors, okay. Okay, so now we are going to look into the Bloch sphere. So why Bloch sphere? All the mathematical understanding, mathematical analysis of the quantum computing. So as I said, so Bloch sphere, higher value 1 0 is ket 0, and here it is ket 1. Okay, and I can take and I can result any vector from these basis vectors, and that is called as psi. The condition is this one, alpha square plus beta square equal to 1, and this point, the collection of these points will form a sphere that's called as Bloch sphere. So no need to worry about this mass, but if I just show you, see, this is the Bloch sphere. So here bracket 0 means qubit 0 and qubit 1. So remaining all common. See here, if you see some combination of this and this is a point here. Similarly here also, some proportionate of 0, some proportionate of this. So this is one point here. Similarly here. So like this, each point on the sphere corresponds to a valid qubit state. Any point you take, any point here you take, that is a combination of this and this, combination of this and this. To understand, to visualize, like this, Bloch sphere. So if you see, of course, formula is also there, but I don't want to go deeper. Okay, so if you see here, this is not mathematics, but in the introductory class, all these things are not required. Now you see how I can represent any value. So superposition value, see, this is 0, this is 1. If I draw any point, so these are all the various values. Okay, so how to represent? How I can represent psi? That is a superposition value, which is equal to any of these curves. Tell me what are the values, how many values I need to represent a point in a globe. Tell me how many values I need to represent a value in a globe. Anyone? 3. Okay, very good. See, in if you want to send a location, what are the values? How you represent a value? It means location on Earth, latitude and longitude. Same here. So when you do the superposition, that will result into a point, and how you will represent that point is what we are studying. So this can be a representation, that means the combination of these two. This can be a combination of these two, but how you represent these points? Okay, so see here, this is the North Pole. See here, 0. This is the North Pole. This is the South Pole, 1. This is 0. So if I do, see, this is the point here, which is a combination of these two, psi. how to represent psi. That is the qubit state, purple value. So purple value is superposition vector, like this. Now tell me, see, if I want to represent this point, I need two values, same location, every point in Earth, in that mobile camera also says that latitude and longitude, same thing. Now tell me here, what is latitude is representing and what is longitude is representing. Do I need both the values or any one is sufficient? Can anyone answer? Or okay, first tell me what latitude in this image, what latitude is representing and what longitude is representing. First question. Second question, why we need longitude? Why we need longitude? That means phi. Tell me. See, this is just +2 mathematics. Okay, we are just looking into the various mathematical operations. How I can visualize the superposition points. Okay, everything is mass only, +2 mass. Now tell me. See, this is also one of the example. This is 0, this is 1. So you have this point, you have this point. There is a point here. Now, what is the theta latitude is representing, and what is the longitude representing? Can anyone tell me? Same here also. And what is the role of longitude here? Any mathematics professors? What is the role of longitude? See, what actually we are studying? We are studying when I take a combination, superposition of the 0th bit and 1 bit. If I take superposition, that means some proportionation of 0, some proportionate of 1, somewhere the line, the resultant value will be, okay, somewhere in the sphere. How to represent that sphere, how to measure that sphere is what we are studying. And based upon the condition that alpha square plus beta square, the coefficients value equal to 1, this will be a sphere, like a globe. In a globe, any point we need two values to represent, that is latitude and longitude. And what this orange is representing, longitude, and this is latitude. Now can tell me what actually they are representing. What latitude is representing and what longitude is representing, just by looking into the diagram. Anyone? Any mathematics? How many mathematics PhDs are here? Mathematics professors? Okay, someone pinged. Where I can see the message? Okay. Krishna Rao, Lakshman Rao. Okay. Probability of 0 versus 1, very good. The phase of the state, very good. Very good. So, what it means? See, this is 0, this is 1. So, I found a point, the superposition point here. So, if I draw this line, this is the theta, latitude. But if I rotate this, now, if you assume a 3D sphere with maintaining just this theta relationship, I can rotate this same with like this. Suppose if it is high, some value, say theta 2. By just keeping theta 2, I can rotate it around the equator like 360 degrees. So this is how far you are from that 0. but the point can be here, the point can be here with same angle. Same angle, I can just rotate. It can be here or it can be here, same angle. So same theta, same theta. So from ket 0, if there is a line theta, then if I just move in the 3D space, this is 2D, right? So now here, if I just move in the 3D space with just theta, I can just keep on without touching these two, maintaining same angle. I can just move. So this is ket 0. Suppose this is ket 0. This is ket the resultant value. The angle is theta. Now I can just move by keeping the same. I'm just moving. Angle remains same, but that is what the longitude says. So see here, when angle is, so angle is like this. Okay, this is theta, and this line is, the point can be anywhere with same latitude. The point can be anywhere with same latitude. Which point? Either this or this or this is what longitude says. So if I create a superposition values from qubit 0 and qubit 1, I combined them to form a superposition value. Where is that point in the sphere? So to represent that, I need two values, that is latitude and longitude. So how I can compute that? By using this formula, cos theta by 2, the angle. When you have theta, okay, so the theta you have to substitute here. That's a big mathematics. Okay, so why is it so? I explained here. Okay, so that is how you will, but you just remember the formula. So the resultant is always cos theta by 2 polar coordinates, e to the power of 5 into sin theta by 2. So this 5 is the longitude, theta is the latitude, and this is what the resultant qubit. Okay, let's go to some interesting example. Too much theory, and almost we came to closure. 8:30 is over. So let me explain one example. These are all the circuits. Okay, so the way the AND gate and the NOR gate, those gates are there, right? Nothing will work here. Okay, so the circuits are completely different. The way we circuit the operations, everything is completely different. See, controlled NOT gate, we never seen that. Hadamard gate, this is one type of a property. Okay, controlled NOT gate is one type of a gate, and based upon these two we can create a circuits. But see, AND gate, NOT gate, NOR gate, those are in classical computing. Here, as my data got changed, now my data is a basis vector, qubit 0 and qubit 1. So at a time, so 0, 1 is one input, or 1, 0 is another vector. So two values are now I have to process. Okay, so one example I want to give you so that you can appreciate the parallelism. One second. So you can appreciate the parallelism in quantum computing. So let me show that example. See, the power of quantum computing is parallelism. Okay, parallelism means at a time I can handle multiple values. What is meant by handling multiple values? If I want to apply, say, suppose there is a for loop of 1 crore values. What I want to do, I just want to go to say, take a value, add 2 to it. First 1 crore numbers I want to take, and I want to just add 1. So here, is there any way to is there any way that I can do parallel in classical computers? My question is, I have 1 crore numbers. Those 1 crore numbers, I want to add just 1 to 1 crore numbers, first 1 to 1 crore. Just I want to add the plus 1 to it. That is my question. That is my problem. How to do that? Okay. So if I explain this, then you can understand. So if you see, we discussed this superposition, entanglement, and interference. Okay. So see here, the power of quantum computing is all about parallelism, superposition. in that the main thing is superposition. We thoroughly discussed and visualized also. See here, allows massive parallel computation. Quantum computing, the heart of quantum computing is parallelism, and parallelism is achieved through superposition, which is nothing but addition of two qubits. And that addition indirectly, see, if I do, suppose if I have two values, 2 to the power of n. So if n equal to 1, I have two values, one is 0 and 1. If I have n equal to 2, I have 2 square, 4 values. So rather than working with 4 values one by one, what I can do, I can create a variable with all 4 at once. So if you see here, see quantum computing, what is the crux in one line? If I say quantum computing is all about harnessing the weirdness of quantum mechanics. See, sometimes there is no proof. Okay, so quantum computing to solve certain problems exponentially faster than classical computers. That's why we have to go for quantum. So I want to say one simple example. See, I have a function x plus 1. So what I am doing, whatever may be the input I receive, I just want to add 1. Suppose, say, just looking to from classical point of view and from the quantum computing point of view. Say I have the input, the x can vary from 0 to 1 crore. 1 crore values are there. So first 0 will come, the output is 1. Like this 1 crore values, I want to print the output. Okay. Now, how the classical computing will do? Say one by one, for loop. It's a for loop. Correct? Now, how quantum computing will do is, see here. Say, now we have 2 qubits. 2 qubits means 2 to the power of n, which is equal to 2 square, which is equal to 4 values. What are those 4 values? See here. 0, 0, 0, 1, those values. Assume that those 4 are like this. 0, okay, 1, 2, 3. Superposition, see, superposition is the heart. Superposition over input. So what I am doing, all these 4 values, I combined together into a single variable. That's what I am telling. So it's not possible to store all values together in a classical computing. Whereas in a quantum computing, this value, this, I can store. Also, I can apply the function at a time. How I am doing? See this. First register holds 4 possible inputs at once. That is the quantum computing. That's it. If you understand this line, that is quantum computing. Remaining all are stories. Each register holds 4 possible values input at once. I can hold multiple values at one. This is 4. Now we are bringing 156-bit quantum computer. That means 2 to the power of 156 values I can process at a time. That is the power. Okay. But I have taken, simply for understanding, I have taken 4 bits. Now see, second register is blank 0. That means, see, this is first register, this is second register. Say this is some dummy place. No need to worry. If you go to next step, I want to apply some function. As I said, take any value, I want to add 1 to it. In case of quantum computing, see, this is f of x plus 1, right? So what I am doing, I want to apply this function. What it implies, okay, whenever you take, first I am taking 1 input, the x is the input I am taking. This is the temporary space. What will happen? The output is this x, okay, and I am applying x plus 1 to this x, that I am storing it here. No need to worry. You see now. When I apply this f of x, what my psi1 contains? These values, 1, 0, 1, 2, 3. This is the temporary initial value of some temporary storage. Now you see, x is what? This value. I am taking at a time 0. This x becomes 0. This is a temporary space. Now what will happen? that will be output into 0, because this is 0, this is 0. Whatever x is there, I am applying this function and I am storing into this place. That means the next place. What is the next place? This one. What is that value? Adding 1 to x. What is x? X whatever you pass. So if you pass 0, x plus 1 is 1. Okay, so this is the input. This is x. This is x. This is a temporary storage value. What it will store? On this x, f of x, I am applying x plus 1. The resultant value I will store it here. So that variable I am just storing it as a default value 0. This is 0, my value. So x plus 1. So for 0, 1, for 1, 2, for 2, 3, for 3, 4. So if you see here, 0, 1, 1, 2, 2, 3, 3, 0. So what had happened? See, apply this to the whole superposition. So for the entire superposition, once I create a superposition, at a time, I can parallelly apply this function. So 0, it became 1, 1, it became 2, 2, it became 3, and 3 plus 1, 4. Okay, so that is at a time. So because I have the capacity to store for all multiple values at once, as I said, this one line equal to quantum computing. That's it. I have such facility so that I can represent all values at once. Say in Python also, if I have any list, so what I can do, x of, say suppose x of 10, what will happen? All values till 10. Okay, which is not there in C and C++. So Python is providing such facility. I can do subsets. Same here also, quantum computing is providing such facility. I can store multiple values together, and if I apply that function, any function I can take, and I'm applying that function to the input. I have to just define the function. What is the function? X plus 1. So instead of the x is this value. What is the output? Applying this x to f of x. What is that? X plus 1. So it is applying x plus 1. So this will see in one step, the machine has applied f of x to all inputs simultaneously. So this one line and this one line, if you understand, then you are done with quantum computing. See, every branch got updated correctly. So 0 is 1, this one, this one, this one. Okay, so that's it. All these things, see, all these things we discussed. Some theory, okay, so you no need to worry about much. So everything, all basics, mathematics, everything I have explained. Okay, vectors, everything. Okay, so we have to take support of electrons to represent the data. Okay, so electrons, photons, etc. They are having the properties to store multiple values together. So all these things we studied, except the circuits, but it will take time. We no need to in advance. Okay, in advanced case we will study. So this is what end-to-end introduction about quantum computing. Okay, hope you got some fair idea what actually quantum computing, what not a quantum computing. Okay, where we can use quantum computing. Okay, and what is the representation of the data, the basis of the data, and the visual representation of the data, what is meant by superposition, and what superposition makes the quantum computing different, and how you can apply superposition. Okay, so hope you got an idea. Okay.
Yes,
okay.
sir.
Thank you.
Thank you. Thank you, sir. So in participants, if you have any doubts, please ask. Thank you for your enlargement session, sir. Class of computer and introduction to quantum computing. Participant, if you have any doubts, please ask. Anybody? Now you can unmute yourself and you can ask.
Sir, I have a doubt.
Yes, please.
Where you showed the representation of a qubit in the block sphere, it is cos theta by 2 plus e power I phi sin theta by 2. I want to know how those things came up there.
Okay, see that. Let me show you. It's completely polar coordinate system. Okay, so See here. So block sphere. So how we are going to represent the data? So if it is here, okay, so this is 0, this is 1. Suppose if I get this point here in the polar coordinates, how I can represent it? Okay, so somewhere I see here. So by using Euler's formula, e to the power of I theta. Okay, so this how I can represent this vector r into e to the power of I theta. Some complex mathematical parts are there. Okay, so somewhere see phase, see Euler form. I have explained, like if you are using a complex network representation or polar coordinates, either see how I can represent from x how much distance it is, say 5 units. So the line is 5 units. That is one representation. Another representation is theta representation. What is the angle from x? So if I use angle, so polar form will come into picture. So what is cos theta? See, horizontal representation. Either I can go with rectangular representation or a polar. Okay, so r I theta. Then how I can represent this one? See, I'm r units out at angle phi. So that is how you can represent the coordinates. Okay, so I clearly explained the math behind this one. Okay, but it is some, see, okay, all those things, north pole, jet pole, how you can use psi, why we have to use that. But for introductory course, introductory session, that will be complex math, so I just touch upon it.
Thank you, sir. If anybody.
In the last slide, we discussed about the register of 2 bits, and there we saw that 1 by 2 initial state 1 and the initial state 0, and then 2 and 0 likewise. What my doubt is that, are we taking the initial state first and the updated state next?
Which one? Here in the
last slide.
Here. I'm keep on adding the new content, so those are not in particular order. This one, right?
Yes, this one, sir.
So this is, see, so when you give x as a input, the meaning is, if you give any value x as a input, okay, input means the value register and place register. Two things are there. Okay, so which contains, it is like this, x comma underscore. So x contains the value. This is underscore. Underscore means you can replace, you can add any value later. So this x is this one, this is the placeholder. If to this function, if you pass this as an input, what is the output it is giving? The x will be as it is, and in the placeholder, I am replacing the f of x value, which is nothing but x plus 1. So this x represents this value, and f of x value is this one, which is equal to adding plus 1 to this, adding plus 1, which is nothing but the function operation.
But if it turns out into a 3-bit register, then the same applies.
Same thing, 0, 0, 0. What is 0, 0 representing? 0. So that will be 0 here. Instead of 0, 1, 2, 3, I will have 0 to 8. That's it.
Yes. Okay, thanks.
So those many values, either 3 or 8 or 2 to the power of 128, it can do parallelly. Same. Why? Because I can store it, and then I can apply the function at a time parallelly. That's it. Single step. For all those functions, I applied the function. Whereas in case of classical computing, so for I equal to 1, I less than or equal to length of the array I plus plus. And then what I will do, A of I equal to, I will take that value and then I will add plus 1. I will implement the function. Okay, one by one, I will keep on looping. Here it's not like that. Single line statement. That's it. Okay.
Thank you.
Okay.
Sir, thank you.
Sir,
Thank
last
you
one,
very
sir.
much, sir.
Sir,
Yes, yes.
hello.
Yes.
Last one, sir, in the same superposition example. Last one, 3 comma 0 is there. What is the significance of that 0, sir? Last one. Why it will become 0?
And that's a value. That's a mistake. That's a value only.
That's the value only.
Plus one value. What is the input? We are adding the plus one. That's it.
Okay. Fine, sir. Thank you.
Okay. Any other doubts
Sir,
from anyone?
sir, thank you, sir. Chandrasekhar, sir.
Okay. Thank you.
for your acceptance and for your valuable session. To dear participants, tomorrow also same time, feedback link is there. You can fill that feedback link. That is considered as attendance. Sir, thank you, sir. We will wind up the session. You can leave, sir. Chandrasekhar.
Okay.
Thank you, sir.
Yeah, thank you.
Nagendra, sir, shall I end the meeting, sir?
Madam, close this meeting.
Okay, sir. Thank you, sir.